So then let's get started. Pardon? Ah, good. So this is the 1 week where we kind of have combined lecture notes with last week. So the chapter that I had uploaded, what would have that been, chapter 8? That kind of covers both types of topics. And the exercises in there are mainly about causal reasoning. So you could go back to that. So that's why there's no lecture notes for this week, but the slides will be there. Yeah? Okay. So first of all, before we start, AT4 is coming up. AT3 results are also coming up. It's a long one. It really requires engaging with all of your answers. Yeah, and I think we're all in similar situations for different reasons at this point, so I will get this to you as fast as I can. Definitely before you put your answers in. There have been questions as well from some students about the exam. So what is going to be on the exam? Is there going to be a sample exam? How can you get an idea of what you have to do on the final exam? AT4 is actually very similar to the structure of the final exam. So obviously different content, but same types of questions. Even the order of the questions is going to be the same. So you can really, as is the weighting mostly, so you can really, by looking at AT4 and working through it, that's an excellent preparation for the final exam as well, right? There's also going to be a sample exam that we'll upload and probably look at together in the last tutorial, so that will be kind of a third example or a second example in addition to AT4 that will help you prepare for the final exam. You can also look at our unit guide, which gives you, so the description for AT4 in the final exam is the same, and that will also give you an idea of what exactly you have to do. So I recommend going back to that as well. Okay, so what did we do last time? Last time we looked at a kind of a new type of inductive argument, and we have been using inductive argument in a specific sense here, namely to refer to arguments that move from a sample, from a subgroup, from a subset of observations or people to a claim about a larger population, a larger group. So the question is always going to be, or the assumption is always going to be, given that we have observed a certain property, a target property, in the sample, can we assume that that same target property is also, will also be present in the whole population? And we had distinguished that type of an inductive argument moving from a sample to a population from arguments that are inductively valid, in the sense that an inductively valid argument doesn't guarantee that the conclusion will be true if the premises are also true, but it does make it more or less likely. Just to remind you of that relationship, we had inductive arguments in the sense of moving from a subgroup to a whole group to a population, would then be distinguished from deductive arguments where you're moving from a population to a sample. All elephants like chocolate, so this one also does. And how does that relate to inductive validity? Well, inductive arguments that move from a sample to a population of this type are always only going to lead to true conclusions with a certain probability, right? It's never guaranteed that all are going to behave in the same way as the members of the sample. By contrast, deductive arguments moving from a population to a sample to a subgroup can either be deductively or inductively valid. So that's kind of the thing that you need to know there in the background just to keep those concepts straight. So how do you decide about sample sizes? We had looked at two different types of questions. We had seen that for random sample, we would expect more variation and especially atypical or unrepresentative results in smaller samples. So a larger sample is going to give you better, more representative results. That's kind of common knowledge. That's not really surprising, but problems arise when we have non-random samples. And those were the examples that we had seen as well. You can sometimes have very large samples, right, the Literary Digest poll or something like that, where results are still off. Why? Because the sample itself is going to be biased in some way, shape, or form. So there's some kind of background knowledge and theory about what the expected type of variation in the target property will be, and that type of thing is going to be necessary. So that's where things get tricky. And finally, we had looked at a number of possible biases, so self-selection biases, right? Any time that people are asked to call in with answers, for instance, a radio poll, or they are asked to maybe participate in a questionnaire online, so that's likely to just reach, well, certain numbers of people. People who respond are likely to have strong opinions on the matter being discussed. And similar effects are obviously also going to hold for kind of commentary sections and articles, right, reviews. Now, this is something that we all know, but we're kind of still often misled by such extreme opinions that we're confronted with, but they're all kind of similarly affected by self-selection bias. And a similar problem might also hold even if researchers have selected a sample, but they're extremely high non-response rates or low response rates. There might be a similar effect of self-selection going on in the background. There's a general problem of samples being selected based on availability. This holds true in science. I give you the example of the weirdest people in the world, right? People studied for psychology in psychology are predominantly psychology students in certain countries. Not clear that they're representative of the population as a whole. They might actually be quite weird. In some ways, similarly, we tend to be misled by how easily we can recall certain types of information or certain types of experience in making kind of general claims. So there are a lot of things to consider here. So moving on, one last thing that's going to connect us to today's topic. You might wonder, you know, why are we talking about all of this? And she was giving us all of these old-fashioned examples last time, you know, U.S. elections, what, from the 50s and 60s? Come on, big data, internet would seem to solve that entire problem, right? Now we have suddenly, or researchers suddenly have access to huge amounts of data. And basically, ideally, the idea would be that here you no longer have to sample, right, subgroups of information. You just have access to the whole population. So this whole question that we've been talking about, is the sample representative? How was it measured? And so on and so forth. You can basically get rid of that by just pumping enough data into your study, right? So that's the idea. So why were we discussing all of this? So here's an implementation of the idea published in Nature, highly respectable, obviously. So an attempt by Google to use search engine queries. So basically, Google searches for terms that you would expect to be related to the flu, headache, joint pain, suddenly feel extremely tired, or whatever. So these types of Google searches, and they were trying to use these data to predict the pattern with which the flu would be spreading in the U.S. Why? Because it's known that there's a correlation between such searches and people actually turning up at their for doctor's appointments presenting with flu-like symptoms. So the idea would be that would allow researchers to predict the spread of the flu and to do so extremely quickly, like with a time lag of a day. And that would be exactly this type of an implementation of just killing it with data, not even going for theory. So why is that attractive? Every single data point would be captured, highly efficient. It would be extremely fast and extremely cheap. It would especially be much, much faster than kind of conventional predictions, which would take kind of a week to get to. Don't have to worry about the details here, but that's obviously going to be much too slow if you're really interested in the spread of a disease. And really attractive for today's topic. You can do it without a background theory, right? It's a totally stupid algorithm, basically. You don't have to have a theory about why search terms are correlated with the spread of a disease. It just, you know that they are and you're done, and you don't even have to talk about causation at all. Great. So today's topic is done. Does anybody know how this turned out? Badly, right? So it doesn't work. So here we have the criticism in science. So everything I've been saying so far has been setting you up, right? So what happened, this algorithm using big data actually radically overestimated the occurrence of flu-related symptoms by more than twice as much. They predicted more than two times as many doctor's visits than actually occurred, and of course then kind of the conclusion, the skeptical conclusion, the smug conclusion is kind of going to be, well, even if you use big data, huge amounts of data, you can't do it without theory in the background. Yet you still have to have these same considerations of sampling and also causal connections in the background. And the reasons for this are old, right? So we have new technology, but this is kind of like literary digest poll all over again, right? You can even have bias in huge samples, so which types of people conduct searches, how do they conduct searches, what are the searches caused by, maybe scary reports, maybe reports about this interesting new technique being used, whatever. Then, of course, also, as we know from internet searches, if certain keywords or chains of keywords are popular, or if you've used them in the past, then the program will suggest it to you yourself. So it's kind of moving the goalposts and actually biasing its own results, and so on and so on and so on. So bottom line is you can't do it no matter how many data you pump into a theory. It's an illusion that you could do away with this whole sampling problem, and it's also an illusion that you could do away with actual causal reasoning. So these old cases that I was presenting, actually they happen again and again. So that's why we need to talk about causal claims, and that's what we're going to do for the rest of this week. Very simple definition. What is a causal claim? What is a causal statement? Well, it says, it makes an explanatory claim about why something happens, linking a cause to an effect, right? The effect happened because the cause was there, right? Or because of a certain cause. So that would be the background. So if you look at these 6 examples that we have here, which of those would not be causal claims? So the first question is always going to be, can you detect causal claims and distinguish them from non-causal claims? So which of these doesn't qualify by the definition that I just gave you? Any candidates?
2, 4, 5.
2, 4, and 5. Do I have other suggestions about this one?
6.
Something about preventing. So is 6, if we start, or if we go through them actually one by one, right? We have 1 gives us a because statement, right? So that's quite obviously an explanation of something else, right? So that answers a why question, so that seems to be a causal claim. this one is kind of a no-brainer as well because it gives us the word causes, right? So that's a sign that we're talking about a causal claim. Likelihood. Anybody can explain why that's not a causal claim? So that's obviously not.
Correlation is not saying because they're shy, they are more likely to develop test anxiety. It's just saying shy children correlate with those who have test anxiety.
Right. So it's not really connecting that in any meaningful way. It's not really giving, it's really just stating a correlation or a co-occurrence of two things. It's not really even attempting an explanation about why that is the fact. What about these two? So there was some hesitation in saying, those don't look like causal claims. We have a tight link or a strong association or something like that. Are those the same as example number 2? So linking and association, we'll see that later on. I would tend to say that's not a clear causal claim, right? Because it's not a clear statement that tries to explain something. Sometimes you can also see this, in some of these cases you might also be unsure what is supposed to be the cause of what, right? So with this one it seems that sleeping with shoes, if there was a causal claim being made, would be the cause of a headache and not vice versa. But in some cases of such sentences, it could go in either direction. So that's kind of an ambiguous term, actually, right? So linking and association can sometimes be used implicitly to make a causal claim, but it's safer to probably just treat it as a correlation. And finally, the last one, it doesn't do it explicitly, but preventing is something that's actually being done to bring about a certain effect, right? Or to actually prevent a certain effect. So I would say that that is going to be a type of causal claim. And here are just kind of some indicator words and underlined ones that will help you identify causal claims. So the clearest one that is not would be this one. These probably not, but they're kind of ambiguous terms, right? Okay. Clear so far? So then what do we do about evaluating causal claims? That's then the next relevant question. So consider these two examples. Somebody paints a house, then develops a nasty rash, so must have been allergic. And then we have a second example. The government's economic stimulus program is clearly working to reduce unemployment. Since its introduction, the unemployment rate has fallen by 15%. Is that enough to support a causal claim, or what is the pattern of reasoning here? If a causal claim was being made, how would that be working? Can somebody identify a pattern in that?
Any other evidence,
Mm-hmm.
like just
So,
ties like one cause to a possible effect, but doesn't really, but like excludes any other possible causes.
mm-hmm. So there's no allusion to other possible causes that might be explaining, or supporting the causal claim. In both cases, there is a causal claim, right? So the person, the rash must have been caused by the paint, and the program must have worked to actually reduce unemployment rates, but no other explanation is considered. So what is the evidence presented here in favor of any of a causal connection? What pattern do we have here? So there's a pattern of absence, clearly. Yeah.
You just said one thing happens and then after another, so just
Yeah.
happens in time.
Yeah, so just temporal order, right? One thing happens and then another thing happens. That's really the only thing that is given here in support of a causal claim. Very common type of doing that, not a very good idea, right? New fallacy, the post hoc fallacy. just because one thing happened after another, that's not sufficient to infer that they were actually causally connected, that A actually caused B. And it's tricky because it's obviously going to be necessary that a cause precedes its effect, right? The cause will have to come before the effect, but just having that is not going to be enough, right? So we can't rely on mere temporal order to infer a causal relationship. So post hoc fallacy is going to be one thing to remember and one way to evaluate possible causal claims or criticize them. So then what is mere correlation, and how does causation relate to correlation, and how do we move beyond that? And to do that, we first have to understand what correlation is in the first place. So correlation really is just a relationship between two different variables such that they both occur roughly at the same time, right? It's just a co-occurrence of two different things, two variables, where a variable is going to be something typically that can take on a number of different numeric values, right? Such as height or weight or income or something like that. Or even something like yes or no, 0 or 1, or something like that. Yeah? So first of all, that's what we're going to be talking about, variables and different values. And then we can look at a kind of a toy example to see how such a correlation might work. So we might have a number of individuals, a number of people, and be looking at two different variables, weight and height for those people, and then we'll assign a number of values, so pounds or kilograms and centimeters or something like that, to the two variables. And here's really just using that to give you two technical terms when talking about correlation, or to distinguish two different kinds of correlation, where the first is going to be a positive correlation, right? Higher values of A are going to also be correlated with higher values of B. In that case, people who are taller are also going to tend to be people who weigh more. Whereas a negative correlation is going to say high values of one thing correlate with low values of the other thing, right? People who are very tall tend to weigh less in that case. Doesn't seem very intuitive, but that would be the negative correlation example. Yeah? So just to kind of know what positive and negative correlation is. So then where do we go from there? Then we can start investigating the strength of the correlation, right? We can chart it into a graph using those 7 data points that we have. 7 is very little, right? So we would expect quite a lot of variation away from the average results because it's a small sample. Now, if we use something like a larger sample, then we get exactly what we would expect. We have height and we have weight, and there seems to be a strong positive correlation that's happening there, just visible through that clustering. Yeah? So that's not rocket science. That should be fairly clear. Yeah? Okay, so that would be one way of depicting correlation. Here would be another way of depicting it, where you would be, for instance, looking at amount of CO2 in the atmosphere and temperatures for a given year, right? So down here you would have the timeline, CO2, and over there global temperature, and then you would get 2 different graphs, and you could see that they behave roughly in the same way, again suggesting that there is a positive correlation between the two. So that would just be another way of depicting that. Yeah? So what is it that we get here? If you look at that, what is this telling us? If you consider that graph. use what I just told you? Who could translate that or explain that? What's going on there?
The more hours spent watching TV, the lower the
Yeah.
average rate point average.
Yeah. So what kind of correlation is that?
Negative.
So a negative correlation, right? Higher values of TV, but watching correlate with lower grade point average. Terrible finding, right? Nobody wants to hear that. Okay. So that's just kind of to explain how that works. Then we have strengths of correlations that can be different. So typically positive correlations would be numerically described like this, right? In the middle you would have none at all, so a value of 0. 1 would be perfect positive, -1 perfect negative. That's typically not something that you will find. So again, when you're thinking about causal claims and evaluating them, I would say it's not enough to say, well, it's not a perfect one, right? Or it's only a very probable relationship. It wasn't really found in all individuals. That in itself wouldn't really be enough to criticize a claim, right? So typically the finding is going to come in degrees, different levels of strength. I'm just saying that because that's something that I sometimes see students doing, right? It's not enough to say it's not always found, it's not a perfect correlation. We shouldn't expect these extremely strong results from science. That's just not how it works. Okay, but that would be different ways of depicting strengths of correlations, positive and negative. And finally, we can play the same game as well if we don't have numeric values, if we don't have a concept of higher or lower for these types of examples, then we would just speak of categorical variables, and again, we could measure the likelihood. So living in Melbourne, Sydney, Canberra, or something like that, that's not a matter of more or less, that's just a matter of yes or no. Yeah? So categorical variable would refer to that. Questions so far? So that's just a little bit of literacy on how to deal with correlations or statements of correlations. So how do they relate? We now roughly know what correlations are. How do they relate to causal claims, and how can we actually move to causal claims when we have something like this? Well, step 1, identify whether a causal claim is even being made. Right? In that first example, drinking habits of several thousand men, so and so many percent of men and so many percent of women are binge drinkers. That's not stating any causal connection. That's just stating percentages, frequencies of binge drinking. This one is, again, this kind of lazy description, lazy reporting, right? There's some kind of link. It seems to be plausible and somehow implicitly intended that there's a causal link, but it's not really saying that, right? So there we would just want a bit better writing, and this is also a tip for yourselves. Don't try to protect yourself in writing by saying there's a link. I'm not really committing to it. Try to be specific in what you're saying by saying what kind of a link it is. Is it causal or not? So that's step 1. And then we have something like this. So we have a causal claim. How do we get the correlation to actually support the causal claim? So watching TV is somehow associated with depression. So can we therefore say that watching a lot of TV causes depression? Is that claim supported? What do you think? Why yes, why no?
No, because it could be the other way around. If you're depressed, you're more likely to watch TV.
Right, so the first question is the direction of the causal explanation even clear, right? And this seems to be an example where there's no a priori reason for thinking that that's the way the causal connection, if there is one, works, right? So there's a very obvious alternative explanation, namely that being depressed causes TV watching, right? And if that were the case, then the causal claim would be wrong. So try and fiddle with the order of the things, of the cause and the effect, and if that works, then you have a problem for the causal explanation. Think about the comparative plausibility of different types of explanations, right? So something like this. There's a strong positive correlation between how well children do in school and the number of books in the house where they live. So we can improve average academic performance by using a free book program to increase the number of books in students' houses. This will work. This will improve their performance. So what could one say about this type of a case? It would seem weird to reverse the order, right? So the claim is being made, putting more books in a house improves performance, causes performance to go up. Could we reverse it, saying if people perform really well, this causes them to have more books? That sounds a bit weird to me, at least, a little bit constructed. Maybe there could.
To do well, have more books. Go out and get more books.
So that would maybe be theory building. That might be something, if you had something like that, you might need additional evidence, right? Showing that. What else could you think? What else might you think might explain that type of a correlation that would not fit with that causal claim? Yeah.
There might be a third factor, and in fact, the other two.
So third factor, common cause, something else is causing both of these things to happen. And these are both effects of something third, but not commonly related to each other, such as parents' level of education or something like that. That would cause one to have higher performance and to probably have more books or something like that. So find different alternative explanations and compare them to each other. Which one is the best one? If they seem intuitively equally strong, then the causal claim is likely not a good one. And here's another one, and this is something that we're very prone, or that is kind of closely related to a psychological fact about humans. So luck. What about luck and chance? Really stable finding, and you can do this with yourselves or also with friends, is think of achievements or good things that have happened, right? Academic life or jobs or something like that. Many people feel, actually most people feel, that success is caused by hard work, right? By actually putting themselves out there, improving, and so on and so forth. It's not just luck. It's actually hard work that causes success. Something we commonly believe. There are good findings on that. So if people are willing to work, this seems to suggest, or a majority of people believe that if people are willing to work, then they're actually also going to be more successful. You can actually change your lot in life, right, by working for it. So that seems to be fairly widely accepted. We're not just lucky. But that's kind of weird, because on the other hand, if you ask people, so again, this is recent Pew research, if you ask people why then are some people rich and others are poor, and it should be that if you put in an effort, you could actually get success. But if you then ask people, well then, why are there these differences, then actually the largest group is going to say, well, it's just circumstances and good or bad luck. It's not actually having put in work. So first of all, there seems to be an inconsistency in how people think about success and how they attribute it to work versus luck, which is kind of weird. Then the even weirder thing is going to be, and this is much too much to look at for now, but this is the interesting thing. Look at this. Why is a person rich? Republicans in America say predominantly because of hard work, right? Hard work got them to be successful, whereas Democrats are going to say, nah, it was luck and advantages. And the same pattern is going to be found for poor people. If you're a Republican in the U.S., then many people you're more likely to think that, you know, being poor is caused by a lack of effort, whereas a Republican will be likely to say that the opposite is true, right? So message here is we tend to have really weird thoughts about how success and achievement relate to luck versus work. People tend to underestimate the effect of luck because obviously we overestimate how strongly we can influence our future, but this is also strongly correlated with causal, with political orientation, which is kind of weird. So that seems to be a psychological fact in how we think about correlation, mere correlation and causation. Background message here, don't underestimate luck, right? In some cases, there's not going to be a causal explanation at all. We kind of tend to be natural causality detectors, right? We try to identify causal relationships between them, but quite often we might also take that too far or be misled by confounding factors, even to the point of being misled by background political assumptions or leanings that we might have. Something like coin tosses or something like that, just random, right? Random variation is also always on the table. So it's not always about finding, if you're evaluating a causal claim, it's not always about finding an alternative causal story. Sometimes there just is no causal story whatsoever. And that can be the case in a wide range of examples. So don't forget that and take that into account. How many people know this one? Serious research, right? This is something that really tells you tells you something about the relationship between temperature averages and number of pirates. Global warming is bad for everyone, right? Among other things, global warming is especially disastrous for pirates, right? Because there's a very strong correlation between rising temperatures since the 1800s and a disastrous decrease in the number of pirates, right? So there must be a causal relation here. So this is kind of a fun thing to look at. It was an open letter designed kind of criticizing that American schools were no longer, or were only going to talk about creationism and not evolution. So this is something there in the background. Weird correlations happen. They're obviously not examples of causation. Here would be two other ones, just to remind you of that point and make that more dramatic. Consuming less margarine seems, at least in the state of Maine, to be strongly correlated with lower divorce rates. That makes absolutely no sense, right? That probably is not going to lead to any interesting causal claims. You can also find, correlation between rising consumption of mozzarella and number of PhD awards in civil engineering, and you can find stuff like that all over, right? This is just for fun. These are just kind of freak correlations between totally random things. Nobody would fall for that. The tricky thing is to evaluate it in cases where there might or might not be and where you don't really know. And you might find that poor science, and sometimes also poor science reporting is like that, right? Saying, oh my goodness, we found this correlation between two different things. This is really exciting. Beware that it could be just something like this, right? So kind of do keep that in the background. Okay, so then That clear so far? So just warning signs might be mere correlation without anything else. Again, theory is needed to get something more interesting. If you look at this example, the study of the incidence of kidney cancer in over 3,000 counties reveals a remarkable pattern. Counties with low incidence of kidney cancer are mostly rural and sparsely populated, and also located in traditionally Republican states. So how might you explain that type of finding if you were looking at that? Hint, you can relate this to something that we've been discussing so far. Healthier lifestyle out in the country. Republicans have healthier eating habits or something. What might be the thing in the background here?
Low population density.
So,
Incidence of kidney cancer, not just the population size.
So what principle does that, if you can think you mean the right thing?
It's a non-random sample.
Yeah, so we would expect weird results for small samples, right? And in rural populations we'll have lower density, so we'll get weird or atypical results. Yeah, so that is exactly the type of thing to take into account, especially because in that case you also find in those areas the highest incidence of kidney cancer, which is again just kind of random. Okay, so to sum that part of it up, correlation on its own is never sufficient. We do need strong correlation to infer causal claims, but we also need something more. You might also not want to take that too far if you're reading the comic, right? But you need something more. And here again are the squashed steps. Identify causal claims. Try to reverse the order of explanation if that works. It's a problem for the causal claim. Luck is not off the table. Always consider that as well, and also always consider third common causes, right? That might be another point. So, last section, good so far? Criteria for causation. And here the general pattern is again going to be something that you already know. So inference to the best explanation. How good is one explanation compared to another? That again is going to be the crucial, or one of the crucial moves for actually consolidating causal claims. And this was the general pattern, right, for inductive arguments. Why would all observed A and B be correlated? Well, because they always are, because they always occur together, and that would best explain the observed correlation, is because it's an incidence of a more general correlation, so something like this. It's just an instance of a more general rule. But that's not yet a causal claim, so then we have to add on to this argument to get something more interesting, and here's how we do it. So what we do here is add, so this is the conclusion that we eventually want to get. We have a limited number of observations. We think that this is evidence for saying that a general correlation holds because this explains the limited number of observations. But we additionally want to say that events of kind A cause events of kind B. And how do we do that? We do that by again making an explanatory claim. If events of kind A cause events of kind B, that would be the best available, or generally the best explanation of why they are generally correlated. So a causal claim is going to provide the best explanation of general correlation and observed correlation. Yeah? So in this case, it would be something like, well, why Why does the kettle of water always boil when placed on a stove? Well, because that is exactly what causes it to heat, and there's no other good explanation for that. Yeah, so again, pretty obvious example, but that's going to be the general pattern of argument here. Yeah? So we actually get explanatory goodness occurring at those two levels. All right. So why is this important, or how does that relate to actual scientific experiments? Well, one thing you're going to have to do is not just rule out any weird additional condition or factor or explanation that could be out there, but first of all, identify the relevant ones. This is going to take, some background knowledge, existing theory, or something like that. How do you determine it experimentally? You've determined different variables that might be responsible for the effect, and you keep them all stable while just varying one of them. And then if you observe a change in the effect, then that would be evidence that the thing that you changed was actually the cause, right? If not, you would just continue that game with the other variables. So hold everything stable, change just one. If you observe a change in the effect, that is evidence for a causal claim. In other words, isolate the presumed cause to see what happens, and then use predictions to investigate it in other kinds of examples. So exactly replication and control over different kinds of conditions would be relevant here. So what do you do if controlled experiments aren't possible, as in almost all of the really interesting things, right? So certainly claims about medical conditions aren't easily investigated in controlled conditions of that form because it would just be unethical. And here are kind of 5 criteria for doing that. And I'm going to, in the last couple of minutes, talk you through a toy example. But these are things to keep in mind, just these 5 points, and use for more complex examples. So strength of correlation, what we were talking about in the beginning, doesn't have to be perfect, but you want it to be strong, ideally statistically significant, or strongly significant. You want it to be consistent across a number of different trials and across a number of different studies replicating the effect, right? Ideally in different populations, if you're talking about people, for instance, are going to provide better evidence for a causal connection. Temporal order is necessary but not sufficient. We've talked about that. Higher doses, the more you have of one thing, the more you will have of the other thing, is typically going to also be a big factor. And finally, consistency with background knowledge, ability to identify a plausible mechanism linking A to B, is also going to be something that says the causal connection actually really nicely explains the observed correlation, right? So these are also all ways of ruling out alternative explanations. So these are the 5 to remember. Yeah, that clear? And just one example of how that plays out. So here we have an example where I think we all grant that there's a strong correlation between smoking and death from lung cancer, but you can't do controlled studies. So how does that play out with these 5 factors in that example? Strong correlation has been established. That seems to be true. It's also a correlation that's highly consistent, right? And I'm not going to go into the basic details here. There's some graphs you can look at home if you want to, but I think this is fairly common knowledge. You get it in different groups of populations, for men and for women, different age groups, different countries, different times, and so on and so forth. So that makes it seem likely that that's that one cause actually increasing deaths from lung cancer. Does it precede lung cancer? Again, that seems to be clearly yes, right? So in both So one had that both for increased lung cancer in men, was preceded by about 30 years by increased smoking, and the same temporal pattern was observed in women. And again, the similarity of time lag seems to support what we all already know, which is completely obvious, but which, if you're a fan of Mad Men, was not always completely obvious to people, right? So this temporal pattern seems to support the causal claim. High doses also seems to be clearly true, right? The more you smoke and the longer you smoke, the more likely a person is to get lung cancer. People stop smoking, that decreases the likelihood that they will get it, and so on and so forth. So that again seems to be a really, really clear and elegant relationship there. And there's a known mechanism, and this is where maybe animal models, as is often said, then comes in, right? TAR would be the common or the likely explanation, the likely mechanism behind it. So that would be just one case of a strong correlation that fulfills all of our answers, that gives really good evidence for a causal explanation. So to sum up and wrap up for today, we have explanatory considerations that come into play. So does the causal connection best explain observed and from there inferred claims about general correlation? If yes, then that looks good for the causal claim. It's not guaranteed, right? Again, that's not something we should expect. But if it's a good and the best explanation, then that's strong evidence for accepting the causal claim with a certain likelihood. And again, you want to consider those 5 factors, so strength, consistency, temporal effects, consistency with background knowledge, and possible underlying mechanisms to further support that explanation. Yeah, so those are the strategies for evaluating causal claims. And that's what we're going to do in the toots. Okay, then we're done for today. See you.